Hello, my name is Justin Licker. I'm a radiation engineer and a supervisor in the Space Environmental Effects Engineering Group at the Johns Hopkins Applied Physics Laboratory. Let's discuss the plasma environment of the Moon and the resultant surface charging effects. Spacecraft charging describes the family of effects that result from free bodies immersed in a plasma, which is some densities and temperatures of free electrons and ions. Now, a free body might be as simple as a 1U CubeSat tumbling around in low Earth orbit, or an exquisite 10 kilowatt telecom spacecraft operating at geostationary orbit. In this instance, however, we're referring to the effects on the Moon as it transits through a variety of plasma environments created by the solar wind and the magnetotail. Note that the Moon itself is absent of an intrinsic magnetic field and a magnetosphere. Also, it's worth noting that the solar wind plasma is not very energetic. Generally speaking, we're talking about single-digit electron volts to kilo-electron volts, or thousands of electron volts, compared to those plasmas that impact charging at geostationary Earth orbit or medium Earth orbit. The graphic on the right illustrates important terms and features that macroscopically influence surface charging on the lunar surface. There's a directionality evident here. The solar wind originates at the Sun, as does ultraviolet energy, which influences photoemission on the Moon. It means macroscopically, on the sunward-facing lunar surfaces, there is an incident solar wind plasma and UV, or ultraviolet energy. There are also charged particles leaving the surface as a result of photoemission and secondary electron yield. The resultant current balance tends to yield a positively charged surface. Although simplified here, this current balance equation is almost always nonlinear, and in fact gives rise to many academic and scientific studies, and PhDs. It's also a good time to point out the importance of material properties on any specific potential value. Not just a description or material composition, but also in the geometry. Characteristics such as secondary electron yield and photoemission yield are not just material dependent, but also geometry dependent. We know from returned lunar samples, Apollo-era surface experiments, and remote sensing that the Moon is an excellent insulator. This means that incident charged particles will stick to the surface and over time cause a buildup of surface charge. Also evident on this graphic is the variations in the plasma sheath between the sunlit and eclipsed surfaces, eclipse being on the wake side as opposed to the RAM or sunlit side. One also notices, even at macroscopic characteristic length scales, the complexities at the terminator where thermal, ultraviolet, and plasma boundaries result in complex and at times highly localized effects. So why does this matter? The processes related to surface charging, which create potential gradients between adjacent regions or surfaces, include the accumulation of electric charge, the release of which is known as an electrostatic discharge, or ESD. ESD represents the release of this stored charge. It is also accompanied by localized, so short characteristic time or characteristic length scales, plasma, high temperatures, and RF or radio frequency noise. The ultimate hazards to space systems and/or human beings is effectively described by the source and the victim model. Here, the source represents the characteristics of the discharge, so its amplitude, the energy released, and so on. The victim then represents any number of elements which might be affected by the discharge, to include things like microelectronic components, materials, communication links, and human beings. Operational impacts range from nuisances, such as a noisy comm link or noisy telemetry signals, to catastrophic, such as sustained secondary arcs damaging solar panels or injury to human beings and astronauts. In addition to the various plasma environments experienced at the lunar surface, surface charging, differential charging, and the resultant ESD can be caused by the movement of lunar dust, so tribocharging. This includes both tribocharging resulting from dust movement, but also the resultant surface modification caused by adhered dust. Validation and verification processes associated with surface charging are well described by modeling, simulation, and testing. Modeling and simulation focuses first on the plasma environments experienced at the lunar surface. As the characteristic timescales associated with surface charging are quite small, and potentials and their impacts can be very localized, models need to consider both macroscopic and microscopic or localized environments. For example, macroscopically is the Moon in the magnetotail. Then, microscopically or locally is the system under study located in a pit or in the terminator region. Models may be run for worst-case conditions or time-varying, dynamic, to predict potentials evolving over time, sunlit conditions, dusty conditions, and so on. There are a number of engineering and physics tools available, but there are also a number of bespoke codes that have been developed within academia that provide exquisite solutions for very specific systems or problems. Risk assessments need to consider the specific vulnerability. This may range from predicting time-varying potentials for science measurements to predicting the ESD risk associated with a moving rover or a human being venturing into a cold, dark region devoid of sunlight. If considered simplistically, we may differentiate testing as material property testing and/or systems-level testing. The former describes a rigorous set of tests, which produces parameters that feed into the modeling tools I described earlier. It includes, for example, secondary electron yield as a function of temperature for complex or non-homogeneous and/or non-uniform materials, such as dust. The latter includes a simulation of plasma, thermal, and/or tribocharging processes in an effort to evaluate risk associated with ESD, or operations in these correlative environments. In both cases, specialized laboratory conditions will be needed to include vacuums, plasma sources, thermal shrouds, dust, and other combined environments. The LSIC Facilities Directory includes descriptions of several chambers and laboratories that may enable tests like this. Thank you for viewing this module.